Welcome to Algebra 1. Today we're going to be talking about conjunctions, which are compound mathematical sentences. The text that this video is driven from is Algebra 1 for Christian schools. It is the second edition. Covers about the same material as the third edition, but the sequencing in the third edition is a little bit different, and the section numbers are definitely different. The structuring of the course is different, but it really doesn't matter what text you have. You can still gain a lot of information about how you work with conjunctions, even if you're not using a BJU press text. So let's go ahead and pray, see what our lame joke is for today, and let's investigate this new mathematical animal called conjunctions. God, I thank you that you are so much bigger than we are, and that you see all of our lives and the plans that you've laid out for us, and that you are at work in our lives, even though we only see what's going on with us right now. Father, I pray that you would be with those on the other side of this video, that you would help them to hear and to recognize your voice, and that you would give them the willingness and ability to walk in your ways, and you would help us to be willing to put forth the effort necessary to learn new material that you place before us. Help me to communicate clearly to my students. And I pray in the name of your Son, Jesus. Amen. Okay, conjunctions and disjunctions. Let me go ahead and write some examples of these compound mathematical sentences on the board. We have x is equal to 4. We also have and x is equal to, or x is less than 6. We have x is greater than 2 and x is less than or equal to 4. Or you could have x is less than -3 and x is greater than 7. I could just make up some of these off the top of my head, but I'm not in a make up off the top of my head mood today. So let's see what else they have. They have x less than 3 or x less than or equal to a -5. X greater than -1 or x less than 8. We have x not equal to 5 or x less than 9. Now both of these are compound mathematical sentences, which means that we have two different things going on. We have x is equal to 4, x is less than 6, x is less than 3, x is less than or equal to a -5. And they're going on in the same sentence, two different things happening. Now, why have I chosen to use two different colors in this particular thing? What's the difference? Yes, that's the difference. These are joined with and. If I could spell a simple three-letter word, that would be good. And these are called conjunctions. You must know that they're called conjunctions. And conjunctions let me wait for a moment until I say that. These are called conjunctions. Now we have also a common connecting word here, which is or. These are called disjunctions. I was just looking at this marker, which is a brand new one, and the tip is all chewed up. It must be difficult to get the cap on it properly. Words that are compound mathematical sentences that are connected with and are called conjunctions. Those that are connected with or are called disjunctions. And there's a very real and different meaning here. Let's take this to the world of your boss at work, or your mom or your dad says, okay, John, we'll do with the dad thing first. Dad is talking to John. He says, okay, John, before I give you the keys to the car tonight, you have to clean your room and mow the lawn. Now, what is Dad saying to you? He's saying you have to do both, clean your room, and you must clean the lawn. Words that are sentences that are connected with and are called conjunctions, and you have to do both of them. Now let's just say that you've gone out and you've worked really hard, John, and you've cleaned your room. However, you did not mow the lawn. Now, assuming that it didn't rain, but you didn't mow the lawn. Are you going to get the keys to the car tonight? Well, if Dad is doing his job, no, you're not, because when you have a conjunction, both conditions have to be met. Dad told you, clean your room, condition 1, and mow the yard, which is condition 2. Conjunctions require that both conditions must be met. Or with math, both of these separate statements here have to be true statements. Okay, now, and I'm going to do another kid job right here. Okay, Sarah, Mom is talking to you, and she says, Sarah, I've got some work for you to do today, but you're getting older. I'm going to give you the opportunity to choose what you would like to do. Either you may vacuum and mop, or sweep and mop, all of the common areas downstairs, or you may scrub the master bath. So Sarah thinks, and she says, well, I really don't want to do either. I don't want to sweep and I don't want to mop, but I really don't want to clean the master bathroom. So she says, okay, Mom, I will sweep and mop the floors. May I go to the movie with my friends afterwards? And Mom says, yes, you can either sweep and mop the floors, or you can clean the master bath. So Sarah sweeps and mops the floors and says, Mom, I've done what you told me to. And Mom says, okay, very good. You may go now to the movie with your friends. Is she upset with Sarah because Sarah did not also clean the bathroom? No, she's not upset, because you only have to meet, there's only one condition that Sarah had to meet in order for the disjunction here to be fulfilled. Only one condition must be true. Only one condition must be met, or only one of the mathematical options here has to be met. Okay? Now these are disjunctions when you're separated with an or, and we're going to be talking about disjunctions again in section 5.6. So we are going to, in section 5.5, only be talking about conjunctions. Conjunctions, again, are mathematical sentences that are connected with and in order for a conjunction to be true, both of those conditions must be met. So let's look at this definition here on page 194. It says, a conjunction is a compound sentence in which the mathematical statements are connected by the word and, which means intersection, and it's symbolized by this caret symbol. So let's highlight this, that it means intersection. Remember, we have intersection in set notation. Means intersection. And it's symbolized with this symbol right here, like an A without the connecting bar. What happens with an intersection of sets? Remember, we had set notation and Venn diagrams, and the intersection of those two circles is that area right there in the middle, which means that the solution, this pen doesn't work, which means that the solution is a part of the first set as well as the second set. So that's what we have with intersection. Now, let's see example 1. It says solve x greater than 2 and x less than or equal to 4. Solve x greater than 2 and x less than or equal to 4. Now let me make sure I copied this down correctly. Okay. Your book says the solution set to a conjunction is the intersection of the solutions to the separate equations and inequalities in the compound statement. When you solve conjunctions, graph each separate sentence above the number line and then graph the intersection of the graphs on the number line. Okay, translation here. We've already said that it's an intersection. It's sort of an overlapping. It's those areas that are true for both this first condition here and the second condition. And we're going to be graphing these solutions on the number line. So first, we want to draw our number line, and guys, I want you to use a ruler and measure this out. There we have a 0, -2, 2, and 4. We have two conditions that we're going to have to meet. Both conditions have to be met. First, we have x is greater than 2. And we're going to graph both on the number line. Graph both conditions, but we're going to graph them above the number line. Both conditions above the number line. So we sort of have an imaginary number line floating above it. X greater than 2 means that we are not going to include 2 as part of that solution. It's going to be an open circle. Greater than, the numbers that are greater than are the numbers further to the right. So this blue right here is the graph of one of the conjunctions, of one of the conditions of this conjunction. The first one here, x greater than 2. Now we are going to graph the second condition in red. This says x less than or equal to 4. Because this can be equal to 4, it's a solid circle because 4 is part of the solution. And it includes everything less than, I'm so sorry about that squeak, everything less than 4. So what we have done here is we have graphed the two separate conditions of this conjunction above the number line. Now, we said that the solution, that the conjunction means intersection. So we are going to graph the intersection on the number line. That's not spelled. Intersection on the number line. So what do we mean by intersection? We mean those areas of overlapping. So if I have these two markers here, and these are representations of my number lines here, one going to the right-hand side, one going to the left-hand side. Where are they overlapping? They're only overlapping where we have two pins. We've got one line right on top of the other. So look at this, and where is our area of overlap? Well, the only areas here that they're overlapping are between 2 and 4. So our solution, it's going to begin at 2, it's going to end at 4. And the question now becomes, do we use solid circles or complete circles? Is 2 a part of our intersection? Is 4 a part of our intersection? The way you tell that is you look at the area of overlap. You've got a solid red line, which means that 2 is a part of the solution for x less than 4. But the overlap here, this bottom graph, that's an open circle, so this has to be an open circle. We have our overlap in between them. So all of this area is a part of the solution. Now, we had an open circle at 2 because we had an open circle here. This, however, is not an open circle because 4 is a part of this solution, that area of overlap. Open circle at 2, solid circle at 4. This right here is the graphical solution to the conjunction that says solve x greater than 2 and x less than or equal to 4. And you would write this, which I didn't take the time to do. We said that we're going to use that symbol. So this could be written as x is greater than 2 and x is less than or equal to 4. Remember, intersection in set notation was like a wicket for croquet, for those of you who ever played croquet. So you go to that pointy symbol. It's very close to our set notation symbol for intersection. All right, this is our graphical solution, but how are we going to show this using the language of algebra? Now, they say on the top of page 195, choose any number in the solution and substitute it in both statements. And it says numbers between 2 and 4, including 4, are solutions. This includes 2.1, 3, 3.5. Just randomly pick a number here. Let's just do test of 3. Is 3 greater than 2? Yeah. Is 3 less than or equal to 4? Yes. Well, what about 0? Is 0 less than or equal to 4? Yes, it is. But is 0 greater than 2? Nope. What about 10 up here? 10 is greater than 2, but 10 is not less than 4. So this is not a part of the solution. This is not a part of the solution. So how are we going to define this solution? We're going to say that any number that is a part of our solution, that's not going to show up for you very well. Any number that is a part of our solution is x. So x is between these two, isn't it? So you have x is greater than 2, but it is less than or equal to 4. X is in the middle. We start here reading and we can say 2 is less than x. X is less than or equal to 4. When you have that intersection, we're combining that both, 2 is less than x, which is also less than or equal to 4. That describes the relationship between these. These x's, your possible solutions are in the middle. It's sort of like a barbell. You're lifting x's in the middle and he's pumping iron here. 2 is less than x, which is less than or equal to 4. And if you heard me the first time, I said x is greater than 2, x is less than or equal to 4. This is something that you can read backwards. 4 is greater than or equal to x, x is greater than 2. Just work with these, mull them over, write some, see if you can figure out what's going on if it seems strange to you. Let me go ahead and look at example 2. Your book goes through a check, but we just checked it and said, is it true that 3 is, pick 3. 3 is greater than 2, and 3 is less than or equal to 4. We also showed how this side wasn't true, and this side wasn't true. Let's go ahead and do another problem and see what conjunction we have here that we need to graph? We have solve x is equal to 4 and x is less than 6. Solve x is equal to 4 and x is less than 6. They want you to rewrite this just simply saying x is equal to 4 with your triangle thingy, pointy thing. I'm not sure what that's called. And x is less than 6. So what are we going to do? We're going to graph both conditions above on the number line. The first condition we're going to graph in red. The second condition we're going to graph in blue. And I have 4 and 6 as the numbers, so I'm going to draw an adjusted number line. -2, 0, 2, 4, and 6. And we want to graph both conditions above the number line. So what's our first condition? We have, and we're going to graph it in red, we have that x is equal to 4. How do we graph that? Simple dot. Now, how do we graph x is less than 6? 6 is not a part of the solution, so it's an open circle. But everything smaller than 6 is a part of the solution. So what we have now is we have graphed both conditions above the number line. Next thing that we're going to do is graph the intersection on the number line. Where's the only point of overlap? The only point of overlap for this entire conjunction here is the point x is equal to 4. So this would be the graph of the solution. And the way that we would write this algebraically would be to say that x is equal to 4. And that is the intersection of x is equal to 4 and x less than 6. There's only one possible place where you've got an overlap because we are so severely limited by saying x can have one value and one value only. It can be 4. For our blue condition, we've got an infinite number of solutions going in the negative direction. It includes 4. So x equals 4 is our solution. Let's go ahead and look at example 3. See what we have this time. Example 3 says solve x less than -3 and x greater than 7. X less than -3 and x greater than 7. That and can be written with a caret. Now what do we need to do? We need to graph both conditions above the number line and see where our point of intersection is. So here's our number line. Now, I'm not going to be real particular here. I'm going to say here's 0, here's -3, and maybe over about there is 7. What do I want to do now? I want to graph both of these conditions above the number line. I'm going to have x minus 3, x is less than a -3 be our blue condition, so the solution does not include a -3, but it includes every value smaller than -3. So there's our blue condition. Now, x greater than 7 is going to be our red condition. X cannot be 7, so it's an open circle, but it includes everything to the right. And now this is looking really weird. What's our definition, or what is our requirement for a conjunction? Conjunctions, both conditions have to be met. So is there any place, if I have arrows going in opposite direction in this space here in the middle, is there any place where there's an area of overlap? No, there is no area of overlap, so there is no solution. Or the solution is the empty set. You can write null, you can write no solution. I suppose you could also write the empty set. But the point being that you understand that this is conjunction, which means intersection, which means that both conditions have to be fulfilled in order for this compound mathematical sentence to be correct. There is no area of overlap, so therefore there is no solution. Now, let's see what we have for one more example. Okay, let's see. We have solve x less than or equal to 5. Forgot to erase that. X less than or equal to 5 and x less than 0. And here I'm just going to go ahead and put that little pointy thing. And x less than 0. Okay? Going to do the same thing that we've been doing. We're going to have a blue condition and a red condition that we are going to graph on the same number line. We have 5 and 0. So here's my number line. I have -5. I have 0. And I have a +5. My blue condition says that x may be less than or equal to 5. So I have a solid dot that I graph here above the number line. And I include everything to the left because x can be less than or equal to 5. Then I have my next condition, my second one, that says x less than 0. 0 is not a part of the solution, so I have an open circle. But everything to the left of 0 on the number line is a part of the solution. Now what do? We look for our areas of overlap on our graphs, and we graph that, which is called the intersection, on the number line. This area here does not overlap. Our area of overlap begins at 0. However, 0 is not a part of the solution for our second condition, our red condition, which was x less than 0. So we're going to have an open circle right there. X is less than 0, but it includes everything to the left on the number line, and that is the intersection of these two conditions. So we have met our conjunction. That's the solution. Now, how would we write this solution? We have to have an algebraic sentence. This is the graphical solution. What is this right here? How would you translate an open circle at 0 going to the left? X is less than 0. And that's the algebraic solution to that conjunction. All right, we have one final example that I want to show you. And this is on the next page in your text. And I'm going to go ahead and erase this part of my board because I need a little bit more working space. Page 196 says this. that we want to solve 2x plus 5 less than or equal to 10. 2x plus 5 is less than or equal to 11. And, which is our caret, negative 3x is greater than 18. So we're going to have our number line, and we have to graph both of these conditions above our number line. But how in the world are we even going to know how to set up our number line? Well, looks like we've got a little bit of work to do on these, don't we? With our blue condition, let's work on this one first. We have an inequality that we have to solve. We have 2x plus 5 less than or equal to 11. We need to get this down to where we have x by itself. We subtract the 5 from both sides of this inequality, and we have 2x is less than or equal to 6. Now we're going to divide both sides of our inequality by 2, and we end up with x less than or equal to 3. We're going to be able to graph this up here momentarily. Now let's look at our second condition, our red condition. We have negative 3x is greater than 18. What are we going to have to do here? We're going to have to divide both sides of this inequality by a negative 3. Now there's something that kicks in when you multiply or divide an inequality by a negative number. And what is that? You will remember that when you multiply or divide an inequality by a negative number, the direction of that inequality changes. Now here, so that means negative 3x greater than 18, the direction of the inequality has to switch, and you have x is less than negative 6. This one over here, however, the direction of the inequality stays the same, because while we subtracted a 5 from both sides of the equation, we didn't multiply or divide. The only time that this symbol is going to reverse has nothing to do with negative signs. It has to do with dividing or multiplying by a negative number. So now what we have here is x less than or equal to 3 and x greater than negative 6. So what you have to do, and x is greater than negative 6. What you have to do, that's funny, is simplify the inequalities before you know how to graph them. Now we know that we have endpoint 3 and negative 6 that we're going to be want to be dealing with. So I can have a negative 6, negative 3, 0, 3, and let's go ahead and graph both conditions above the number line. First, I have x is less than or equal to 3. So I have a solid circle at 3, and I graph everything to the left on the number line. Then I have x is greater than negative 6. So I have an open circle because negative 6 is not part of the solution, and I'm going to graph everything to the left of negative 6 on the number line. Now, what we're looking for our solution is what? We graph the intersection on the number line. We're looking for the area where those two graphs overlap. And the area where they overlap here begins at a negative 6, but negative 6 is not a part of that solution. It's an open circle because we have an open circle with the red. The overlapping begins with everything to the right of that number. So we now have the graphical solution to this conjunction. And how would you write that algebraically? How would you write that graph? Describe that graph. You would simply say that x is less than -6, and that would be your solution. So, solving conjunctions, your book says, solve each statement in the compound sentence, which is what we did. We solved each statement in the compound sentence. We graphed both solutions above the same number line, and then it says the solution to this conjunction is the intersection of the graphs, and you need to be able to show the solution graphically and algebraically. So apply yourself to this. If you get stuck, send me a text. Otherwise, ask me a question in class on Friday, and I will see you next time.